So in question 3 we have something very similar to the Young-Slitz experiment in question 2, except this time we're doing it with microwaves instead of visible light, and so the wavelengths are much longer, but the principles are exactly the same. So the first thing it says is that we've got these two narrow slits here and here acting as coherent sources, and it asks us to define what coherent means. So it's very important that you learn this definition, which is that coherent sources provide waves with a constant phase difference. The common mistake is to say that they have to be in phase or in the same phase, but that's not true necessarily. I mean, it can be true, but they have to have a constant phase difference, and that's the definition, and they have to have the same frequency. Okay, so that's the definition of coherent sources, but it's one of those where most of the time when you're thinking about them, you just draw waves with the same phase, but it doesn't have to be the case. So when you're learning the definition, make sure you get constant phase difference. So next it wants us to find the wavelength of these microwaves, and this is the bit of information that it gives us in the question, that the frequency is 9.4 gigahertz. So the relationship obviously that we want is this one. C is equal to f lambda, which is on your data sheet, as is the value of c. Remember, this is electromagnetic radiation, so c is the speed of light. So that's 3.00 times 10 to the 8 meters per second. So we've got f and we've got c, so we can easily solve for lambda. So as always, rearrange the expression first and get lambda is equal to c over f, and then plug the numbers into that. So that's 3.00 times 10 to the 8 divided by 9.4 gigahertz. So you've got to remember your prefixes here. Remember how it goes. Kilo is 10 to the 3, mega is 10 to the 6, giga is 10 to the 9. So that's 9.4 times 10 to the 9 hertz. If you put that in the SI unit, and if you work that out, you get 0.0319, and that will be in meters, because it's the wavelength, and you could round that to two significant figures, given that you've got that. So you could say 0.032 meters to two significant figures. Now for B part 2, we have to state what the difference in path length is for the waves coming through this slit and through that one. And so that just means the difference in distance travelled from the slit to the detector in both cases. And the way you do that is simply to count how many wavelengths there are for each path length. So you can see here, that's 1, 2, 3, 4, 5, that's 6 wavelengths, the path length, and this one, 1, 2, 3, 4, 5. Okay, so the path length difference is just one wavelength, because it's the difference between 6 wavelengths and 5 wavelengths. So the path length difference is just equal to one wavelength, which is 0.032 meters, or 0.0319 if you use the unrounded number. So the same answer you had for the previous part. Now for part C, we have to explain whether what we'll get at this particular point is a maximum or a minimum in the interference pattern. And the important thing is that you explain it fully to make sure you get all of the marks. So looking at this, you can see that at the point where it arrives at the detector, that's in phase with this point, and 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 that point. And you can see that these two waves are also in phase with one another at the point where they start. So this has got the same phase as that, and it's in phase with this, and this, and this, and this, and again with that one. So the important thing is that at that point where it arrives at the detector, the two waves are in phase. And of course you could work that out without picking your way through the diagram like that, just by realizing that if the difference in path length is a whole number of wavelengths, then inevitably the waves will be in phase when they arrive, provided they were in phase when they started. Okay, so the answer is that the waves are in phase when they arrive at the detector. And I think it's important that you spell out why rather than just stating that, because it says explain, and you explain that because the path length difference is a whole number of wavelengths, which in this case is 1, but any whole number you would come to the same conclusion. Okay, so that's the first thing. The waves are in phase because the path length difference is a whole number of wavelengths. And then you have to say, right, well, what does that mean? Well, what it means is that you get constructive interference occurs when the waves are superposed. At the detector. Okay, so notice how all the time in these explaining questions you try and use all the key words. So we've used in phase, we've talked about path length difference, we've talked about constructive interference, and we used that word superposed because superposition is necessary in order for interference to occur. So constructive interference occurs when the waves are superposed at the detector. And finally, we still haven't answered the question. We've talked about everything that happens, but we haven't explained the upshot of that. But if you get constructive interference, then you'll get a maximum in this case in the intensity of the microwaves detected. So you'll get a maximum. So part D now wants to know what happens if we double the frequency of the microwaves. So again, we use this relationship, and remember that C is a constant. So if this is doubled, then this must be halved, so that when you multiply them together you still get the same number. So the wavelength is halved, and that's the first thing you need to state. That doubling frequency means that lambda is halved. And then you don't need to obviously draw this on the diagram, but it's possibly helpful just to make sure you can visualize this to do that. So if the wavelength is halved, instead of this distance being one wavelength, this distance will now be two wavelengths. So in other words, the wave will look like that, and you'll have two complete wavelengths in that same distance where we had one before. But you can see the important thing about that is that it means that there will still be a whole number of wavelengths. Okay, so this path length was 6 wavelengths, so now it will be 12 wavelengths, but it's therefore still a whole number. And this path length, instead of being 5 wavelengths, will now be 10 wavelengths, because the wavelength is only half as big, but it's still a whole number. So the difference in path length will now be 12 wavelengths minus 10 wavelengths. So the difference in path length will be 2 wavelengths, but so long as it's a whole number of wavelengths, they'll still be in phase. and therefore the interference will still be constructive, and therefore it will still be a maximum. Okay, so that's the answer to the question. So first of all, you explain that the lambda is halved, and then explain this means that the number of wavelengths in each path length is doubled. But if you double an integer, you still get an integer. So that means that it's still a whole number of wavelengths. And so the difference in path length is still a whole number of wavelengths. And if that's the case, we've got the same situation as before. So still a whole number of wavelengths means that we get the waves in phase at the detector because they were in phase when they started, and they'll be back in phase at the end of each wavelength. So in phase at the detector, which means constructive interference, which means that it will still be a maximum.